All right, so let's move on to these two exercises, 9.2.12 and 9.2.13. And it seems that people did not realize that these were the key to the Cayley table assignments. We had several Cayley tables that you needed to show either were a group or were not. And these two exercises really were the key that enabled you to do that effectively. So I'll do a couple of those exercises later. All right, so what this says, given two elements, first one says, given two elements G and H, show that G is the identity element of G if and only if G composed H is equal to H, right? So what that means is that in a Cayley table, if you see an entry corresponding to this operation, G composed H equals to H, that tells you right away that G is the identity, right? So what would that look like? That would look something like this. If I had an element G here and an element H here, and we had a result here H, right? Now it's also going to work the other way. It's pretty straightforward modification. If I have an element H here and an element G here, and the result here is H, in both of these cases, this means that G is the identity. G is the identity. Okay, so that's a very useful feature of Cayley tables that you can use in order to identify what element must be the identity of your group. All right, so let's move down a little bit and see what we're going to do here. All right, so we have to prove it two ways. We have to show that, because it's if and only if, we have to show, first of all, if G is the identity, then G composed H is equal to H. So that's the forward direction. And then you have to show the backward direction. So let me go ahead and do the forward direction first. So the forward direction is like this, and this is suppose, just to abbreviate that, suppose that G is the identity. Okay. Then what about G composed H? Well, by the definition of identity, well, that's what identity means. If you have an element that's the identity, then if you compose it with any other element, you simply get H back again. And in fact, you also have H composed G is going to be equal to H as well. Okay. Looks like I went a little bit off the edge there. Let me move over so you can see what I'm doing. All right, so that shows the forward direction. The reverse direction says that if G composed H is equal to H, then G must be the identity element. So I'll show the reverse direction. That's what if and only if says. I have a statement that I have to prove both ways. I prove the one way implies the other, and the other way implies the one. Okay, so we go back and do the reverse implication. In this case, I need to suppose that G composed H is equal to H. Now in this case, we can multiply both sides by H inverse on the right. Okay? Since this is a group, we know that H must have an inverse. So that would give me G composed H. And then we have to compose with H inverse on the right is equal to H composed H inverse. Okay. And we can just call this substitution or whatever you want to call it. It's just doing the same thing to both sides of the equation. Now let's simplify. H composed H inverse is the identity by the definition of the inverse. Okay, and we'll leave this side the same. Let me scroll down a little bit so we can keep track of this. So that would give me that G composed H inverse. I wrote it down too far. Let me move it up a little bit. Whoops, sorry. Got to move back here. So we'll get there. All right, so this gives me same thing on the right hand side, on the left hand side. G composed H inverse. Okay. All right, and that's equal to the identity. Now I can reassociate the left hand side. All right, I can change the parentheses around because of associative property, which is a property of all groups. And as I said, we already know that all of this is taking place in a group. So we have the identity, so this is associative property. Okay. Now here we have our H composed H inverse again. So that means I have G composed identity. And so that's the identity property. And then, I'm sorry, that's the inverse property again, not the identity property, because I'm taking H composed H inverse. Okay, where's my cursor? There we are. Okay, and then finally, G composed identity is just G, that's the identity property. So G is equal to the identity, so that's the identity property. And that gives me my result. I started with G composed H equal to H, and I ended up with G as the identity. Right? So again, this is very useful in the context of Cayley tables. When you have, to show this picture again, when you have a Cayley table arrangement that looks like this, you have a group element, and it has the same element in the same column or in the same row. Okay. So that's 9 to 12. We'll move on to 9 to 13. All right, now let's look at 9 to 13. This one says, show that if G is a group, then for every row of the Cayley table for G, no two entries are the same. That means every entry, if you look at one row and you look across the row, every entry must be different. Now the number of entries in the row is equal to the number of group elements. Why is that? Because you have the group elements listed across the top. And there has to be a group element in the table for every column in the Cayley table. So that means that every row of a Cayley table must have all the different group elements. Same thing with columns. Every column of the Cayley table must have all the different group elements. No two of them can be the same. They all must be different. Right? So that's what we're trying to prove, that all of the elements in the row or column of the Cayley table are different. Okay. So let me just state that in words. So this is 9 to 13. So we want to show that no two elements in the same row of a Cayley table are the same. Okay. Now let's do a proof by contradiction. Let's show that it can't be possible by supposing that it's true. We've done this strategy before. So we'll do proof by contradiction. Okay, so we're looking at one row of the Cayley table, and here we have the row of the Cayley table will have some group element here, so we'll call that H. And here we'll have one group element G and another group element G prime. And if two entries in the row are the same, that means we would have an A here and an A here. Right? So this is a case where the row has two group elements the same. And we're going to show this is not true by contradiction. So we're going to say, suppose that HG equals A and HG prime is equal to A, and G is unequal to G prime. All right, so this would be two different row entries would have the same group element. Okay. Now, if this is true, then what can we conclude? Let me move down. Let me just do it over here. Well, if these two are both equal to A, we can set them equal to each other. That would mean then HG is equal to HG prime. And this is just by substitution. Now, we can multiply by H inverse on the left on both sides. And we can also call this by substitution. Sorry, I keep running off the edge there, don't I? But I think you can see the important part. Let me move it down. Now from here, it should be pretty clear what the strategy is. We want to cancel the H inverse with the H. In order to do that, we need to reassociate. All right? So that would give us H inverse H times G is equal to H inverse H times G prime. And that's the associative property. Okay. Now we're in the position to use the inverse property. H inverse H is equal to the identity. This is the inverse property. And then finally, by the identity property, that tells me that G is equal to G prime. It's the identity property. But look here. Here we have G equals G prime. And here we have G unequal to G prime. So this says G equal G prime. This says G is unequal to G prime because we wanted two different row elements to be the same, the same value. So we have a contradiction. Since we have a contradiction, our suppose cannot be true. So this cannot be true. You cannot have two different row entries have the same group element. So this means that this gives us our result. So two different row entries can't agree. And the column proof is very, very similar. You just turn this picture on its side and run through the same argument. You'd be multiplying by h's on the right-hand side instead of on the left. So again, this is going to be a key fact in our analysis of Cayley tables.